Good afternoon. It gives me great pleasure today to be able to talk to you about work we've been doing over the last 4.5 years or so at Google. That work involves building a distributed database called Spanner. Spanner currently provides most of the critical features you'd expect from a database: schematized tables, a semi-relational data model, general purpose transactions, and an SQL-based query language. This one-line summary I'll give as to why we built the database as opposed to a key value store is that we want to make it easy for programmers at Google to build their applications. We go into a little bit more detail in the paper as to our rationale for this. For reasons of time, I won't be able to go into it in this talk. I should mention briefly that Spanner is running in production at Google as we speak. It's used to hold probably the most valuable data set at Google, which is our advertising database. It replaced the sharded MySQL database that held the same data as of a year ago, and we've been transitioning over the past year. So let me briefly describe the scale of Spanner by explaining a client application that one might want to build on top of Spanner. Let's say we want to build a global scale social network with some primitive features. In particular, we're just going to maintain friend lists and a list of the user's posts. So Spanner provides a single system that looks a lot like a single database, but it lets you shard the data across multiple continents. The idea is that we want to store data across the globe. So in this example picture, we have 4 separate continents. We're storing data in four countries in those continents. Even more complicated than that, we're sharding data thousands of ways so that we can spread the load across thousands of machines in our data centers. Even more complicated than that, we're replicating that data across data centers. So we might replicate the data in the US 3 ways, Brazil 3 ways, Russia 3 ways, and Spain 5 ways. All this is client application configurable. So we want to store data across thousands of machines, tens to hundreds of data centers, millions of rows of database rows. That's sort of the scale we're talking about here. Now, in the paper we described the structure of the Spanner implementation. I won't have time to go into the details in this talk. Again, I'll have to refer you to the paper. What I'll focus on today is the research contributions that we've made as part of designing and building Spanner. So I'll explain the research contribution in terms of a feature. And the feature is, how do you execute read-only transactions across data centers in a lock-free manner? And that feature is supported by a theoretical property that Spanner provides, which is that distributed transactions are externally consistent. External consistency basically says that the commit order of transactions is the same as the order in which you actually appear, in which users actually see the transactions executed with respect to global wall clock time. And Spanner is the first system to provide this property at global scale. Then I'll briefly describe the implementation, which involves integrating concurrency control, replication, and two-phase commit. That integration is necessary both for correctness and for performance. And finally, I'll describe the enabling technology that makes this all possible, which is a global clock called TrueTime. TrueTime exposes uncertainty in the clock by representing time as an interval. So why do we care about read-only transactions? Well, in our social network, suppose we want to generate a web page that consists of my friends' recent posts. Well, we want to generate this in a consistent fashion. That is, we want to make sure that the list of friends that we use to generate the posts is consistent with the posts that my friend put up on their stream. So why does consistency matter? Because you might think that, for example, for a social network, consistency is not that big a deal. Well, you have to remember that for a lot of applications, including social networks, people can use these for ways that you don't anticipate that have real-world consequences. So, for example, imagine that somebody wants to criticize their government and they want to make sure that nobody who might rat them out sees that post. we better damn well make sure that when we generate the web page of this untrustworthy person's friend's recent posts, that we don't show this post P. So how are we going to solve this on a single machine as a straw man? So let's say we want to execute a read-only transaction to generate my web page of my friend's recent posts. Well, the brute force way of doing this is to acquire read locks on every piece of data in the middle of the transaction, and then execute the process of generating the web page. This, of course, is slow. It limits the throughput of the system and is undesirable. What we really want to do is we want to generate a logical snapshot of the database, generate the web page from the logical snapshot of the database, and not block any of the incoming posts. I'll describe how we achieve the logical snapshotness of the database in a few slides. First, let me explain what the real problem is as we scale. So let's suppose we shard the database across two machines, the green shard and the purple shard. And we want to generate my page again of my friend's recent posts. Well, the brute force way of doing this, of acquiring read locks, is doable. But of course, this limits throughput even more because the process of generating the web page is much slower because we have to incur communication costs across the network to get my friend's recent posts. What we really want to do, again, is we want to take a snapshot of the purple shard, and we want to take a snapshot of the green shard, and we want to generate my friend's recent posts web page from those two snapshots. Now, that, of course, is not exactly what we want either, because remember, I argued that we want consistency. What we really want to do is we want to take snapshots that are synchronized in time at two different shards of the database on two different machines, such that we get a consistent snapshot across the shards. And then we want to generate the page from those sharded snapshots. And of course, the problem is even harder than that in Spanner. Recall that we're sharding the database across multiple continents. Within each continent, we're sharding the database thousands of ways, if not tens of thousands to hundred thousands of ways. And then we need to generate the snapshots from the shards scattered across machines, scattered across data centers, across continents. So how are we going to actually do this? Well, first, let me talk to you about version management, because I mentioned briefly at the beginning of the talk that this is a multi-version database. And what we do is we're going to use strict two-phase locking to guarantee serializability of the writes in the database. So, and what we do as part of strict two-phase locking is we'll assign a timestamp to every transaction such that the data that the transaction writes is timestamped with the timestamp of the transaction. So for example, here's a little table that illustrates the evolution of the system for the example I gave. At some time before 8, my friends contain an untrustworthy person X, and X's friend list contained me. At time 8, let's say, we'll get to where the timestamp is chosen in a future slide. At time 8, we want to issue a transaction to remove X from my friend list and me from X's friend list. And then at some other time, 15, we want to read the post P from my posts. And note that intuitively, you get sort of instantaneous snapshotting of the world as you go. You just read the data at the timestamp that you want to get a consistent a snapshot across all this data, right? This is intuitively what happens with multi-version concurrency control. Note that we don't use multi-version concurrency control for writes because we actually want a stronger semantics than snapshot isolation. We provide something which is stronger than serializability even, which is external consistency. But this is the model of the underlying data to get the snapshotting behavior. So how are we going to provide these synchronized snapshots? Well, what we intuitively want is we want some notion of global wall clock time. That is, we want to be able to say, take a snapshot at this absolute time across machines, across data centers. Well, it turns out that this property is equal to a theoretical property called external consistency. And I'll repeat what external consistency means. It means the commit order in which transactions appear to have executed is equivalent to the order in which users can see the transactions executed. So concurrency control, when it satisfies this property, guarantees that users will see something consistent with what they observed. Well, this is actually a relatively tricky property to implement because it involves commit order, global wall clock time. How are we going to actually do this? So the intuition is the following. We're going to transform the problem from one of commit order reasoning to timestamp order reasoning. What we'll do is we'll choose timestamps for transactions such that timestamp order equals commit order. And then the problem becomes, how do we show that we achieve timestamp ordering of transactions equals global wall time order of those transactions? Well, how would we do this in a single machine? How would we assign the timestamps to transactions? Remember, we're using strict two-phase locking, so there's a point at which we've acquired all of our locks. And the intuition is that we want to pick a timestamp that falls in the interval of time during which we hold all our locks. So we acquire all our locks. At some time after that, we pick the timestamp s equals now, and then we later release our locks after we've done the work in the transaction. Okay, and we can pick any timestamp in that interval as long as it's before we release our locks. Now, why does this give us the properties that we want? Well, the two properties that we want, remember, are timestamp order equals commit order. And you can see that by the diagram on the top of the slide. Let's say we have two transactions, T1 and T2, where T1 and T2 conflict on the data that they touch. Since they conflict, it must be the case that the intervals of time during which they hold their locks are disjoint, because otherwise you wouldn't have serializability of your locking. Therefore, the timestamp of T2 must precede the timestamp of T1, since the orange intervals cannot overlap. Now, that was the first condition we needed to transform the problem from reasoning about commit order into the domain of timestamp order. The second condition we need is that timestamp order respects global wall clock time. And that you can see by the bottom picture. Let's say we have two transactions that happen to touch different shards of the database, and they don't conflict at all. But we know that T3 finished before T4 started. This is the key property of external consistency, that if a transaction finishes before another one starts, somebody could see that ordering, and you want the system to preserve that ordering through concurrency control. And you can see by the sort of obviously that when we pick a timestamp that falls within the orange bars, we're guaranteed that the timestamp of T3 precedes the timestamp of T4 sort of by construction because of the fact that we know the two intervals don't overlap. So this is the intuition behind how we're going to pick timestamps to guarantee external consistency of spanner. How are we going to actually do this across machines, across data centers? Because the previous slide assumed we had some global clock where we can just pick a timestamp from that global clock. So what we do is we depend on a system we built at Google called TrueTime. And I'll describe the implementation of TrueTime a bit later in the talk. What I want to get to now is sort of the API. And the API is simple. TrueTime is a global wall clock time that reflects uncertainty in the clock. And it reflects uncertainty in the clock in the form of an interval that bounds the absolute time at which you executed the now call. So what is guaranteed by TrueTime is that earliest is guaranteed to be a time less than or equal to the time at which the event of calling now happened. And latest is a time that's guaranteed to be at or later than the time of the event of calling now. Okay, that's a very strong invariant. This says that we are guaranteeing the bounds on time. And I'll talk about how we make that guarantee later. We'll refer to the uncertainty of this interval as epsilon. So the diameter of the interval is 2 times epsilon. And that'll be important later to remember that notation. So how are we going to pick timestamps given that we have TrueTime? Well, what we do is we acquire all our locks. We pick the timestamp s to be TrueTime.now.latest. That is, we pick a timestamp in the future that is guaranteed to be an upper bound on the actual time at which now was executed. So that guarantees that S falls in the interval with respect to the acquisition of the locks. How do we guarantee that S falls in the interval with respect to releasing the locks? Well, what we do is we wait. We slow down the system to wait out the uncertainty in the clock. So we call this commit wait. And what we do is we simply spin, logically spin. We don't actually sit there in a loop and spin. And we spin until tt.now.earliest is greater than S. So we wait out the uncertainty on the other side of the interval. This is called commit wait, and it should be noted that the average length of commit wait is approximately 2 times the average epsilon. We pay epsilon on the left-hand side of the interval, and we pay epsilon on the right-hand side of the interval. As I'll briefly describe later, epsilon tends to be in the range 4 to 5 milliseconds in the common case. So 2 times average epsilon is about 10 milliseconds, which is an important value because it's actually pretty low. It's on the order of the latency of a disk write. And that's important because we can actually overlap commit wait with real work. So commit wait interacts with replication, for example, in Spanner. Let's say we have 3 replicas. We acquire locks at one of the replicas. We pick the timestamp S. Then we can start our consensus algorithm. We use Paxos, but you could use other consensus algorithms. And then we achieve consensus on the right. And then we check commit wait is done. And after that, we release locks. I've drawn the picture so that commit wait looks larger than consensus costs. But remember, we allow clients to replicate their data across the country or across the globe. So 100 millisecond latency to actually achieve consensus is going to far dominate the cost of commit wait in the common case. It should also be noted that replication has to be integrated with concurrency control here. For reasons I won't go into detail, we actually can't notify the slaves of the fact that we've achieved consensus until after commit wait. Commit wait also interacts with two-phase commit. We can overlap the work for two-phase commit as well. So let's say we have 3 participants. Each of them acquires locks. Well, each of them picks a timestamp using the algorithm I described. The 2 non-coordinated participants log their prepared messages, and then they're done logging their prepared messages. They send prepared back to the coordinator, and they piggyback their values of S on the prepared message. Then the coordinator computes an overall S timestamp, does commit wait, releases locks, then sends a committed message which piggybacks the overall S value back to the participants, after which time the participants can release their locks. So this overlaps the work of logging the prepare with commit wait. Note again that two-phase commit has to be integrated with commit wait because you can't actually send the committed message until you finish commit wait. Let me run briefly through the example of how this actually works with the data representation I described earlier. So let's suppose we have 2 transactions, one where we remove X from my friend list and myself from X's friend list. Well, let's say the 2 participants choose 6 and 8 for their timestamps. 8 gets chosen as the overall timestamp for the transaction, and then 8 gets propagated to the participant. And the write actually happens at 8. So we see in the bottom chart at the timestamp 8 is when the removal of X as my friend happens. And then let's say the transaction 2 happens, and again, let's say it chooses timestamp 15 through the algorithm I described earlier. Well, then the post shows up at time 15. Now, this is the exact same chart I showed earlier, but note that this uses TrueTime to compute timestamps, and we can do this across machines. So this is across the green and purple shards, and the green and purple shards have consistent timestamps even though they're in different data centers. So what I've done is a deep dive into a long chain of reasoning to justify why we want read-only transactions to be consistent even across data centers. I've explained how you need external consistency to achieve that feature. I've described the algorithm of timestamp assignment that gives you external consistency. I've described the TrueTime API and how you can wait out uncertainty to actually achieve all of these features. What I haven't described, and I won't have time to describe, is, for example, how do you actually execute a read in the present? This is a tricky question. How do you ensure that there are no writes ongoing when you actually say, give me the most recent value. TrueTime enables that to happen without any extra magic. We also support atomic schema changes across thousands of shards of a database table, even though the table might be sharded across data centers. Again, we depend on the fact that TrueTime provides us with an absolute clock. We play a trick where we commit a transaction at some future time, so we avoid blocking most ongoing reads and writes. And we also support non-blocking reads in the past for any sufficiently up-to-date replica. And we determine sufficient up-to-dateness by using TrueTime, of course. What I'll describe now is go into the TrueTime implementation and how TrueTime actually gives this guarantee of bounded uncertainty. So this is the basic architecture of TrueTime. In every data center, we have a handful of what we'll call time masters. Most of them have GPS receivers attached. A few of them have atomic clocks on board directly. Any client machine in any of our data centers that wants to use TrueTime merely has to run a daemon that regularly contacts a subset of the time masters. That daemon will contact some local time masters to minimize latency. It'll contact some remote time masters to get redundancy in case the local time masters are down. It'll contact mostly GPS time masters, but it'll contact some atomic clock time masters to get redundancy of different time references. And what we do is we run Marzullo's algorithm, which basically intersects time intervals to determine a time reference. So logically, this subset of time masters gives us a time reference. The time reference will express it as now plus or minus epsilon. That is, the API gives us an interval from earliest to latest, but we actually generate the interval by finding the center and adding and subtracting uncertainty. So we get a time reference that's of an interval that represents the uncertainty from talking to the time masters. Given the precision of GPS and atomic clocks, the uncertainty interval is dominated by the latency to the time masters from the client. So what does the TrueTime implementation look like when we want to invoke give me TrueTime now at the client? We have to return an interval, which is now plus or minus epsilon. Now is the reference now plus the local clock offset from the last time we talked to the time masters. So we have a reference now. And epsilon is basically the reference epsilon that we computed when we talked to the time masters. And it increases at the worst case clock drift we assume for our machines. So let's say we compute epsilon at time 0. We assume that the clock drifts at most 200 microseconds per second. So roughly, we add 6 milliseconds onto the value of epsilon over 30 seconds. Then the next 30 seconds, we talk to the time masters. We compute reference uncertainty again. And again, it increases at the rate of 200 microseconds per second. So this is, in some sense, the magic constant underlying TrueTime for our platforms. What we've done is we've said we will guarantee that clock drift on our local clocks on our machines in our data centers is less than 200 microseconds per second. And I will mention that this is substantially worse than the spec for our machines. I won't tell you, for a reason of confidentiality, I probably can't tell you exactly how much worse it is. So what if a clock goes rogue? Because that's the basic question. If you look at TrueTime, what happens if you violate this magic constant of 200 microseconds per second? Well, what would happen, of course, is the timestamp algorithm would break. That is, timestamp algorithm would assign timestamps in a way that's not externally consistent. But in fact, based on typical failure modes of clocks and based on empirical data from our fleet of machines over the last year, bad CPUs are 6 times more likely to happen than bad clocks. That is, we might as well assume that the TrueTime constant holds true because you're far more likely to actually fail your computation because the CPU is doing something bad to your system. So from that perspective, we're willing to assume that TrueTime is correct. Here's a graph that shows up in the paper. I'm not going to go into much detail about it. The lesson, let me briefly say, this is data taken from thousands of machines across several thousand kilometers and measures the reference uncertainty computed when the client talks to a subset of time masters. The important thing to notice is that the 90th percentile, which is the red line, tends to be close to 0 milliseconds. But there is a long tail. The 99.9 percentile is often up to like 4 or 5 milliseconds. So the worst case epsilon will tend to be 6 milliseconds plus 4 milliseconds, which is around 10 milliseconds for epsilon. That concludes sort of the technical part of the talk. This is related work. I won't dump a whole lot of sites on you. There's a ton of related work in the field of consistency, distributed databases, concurrency control, replication, transaction protocols, and time. What we've done is innovated at the time level and made use of the time interface to implement better concurrency control to provide a stronger semantics. I'll describe a few pieces of future work that are mentioned in the paper. One is improving TrueTime. We believe we can get TrueTime below epsilon, below 1 millisecond consistently through some relatively straightforward mechanisms like better clocks, increasing the polling rate, and so forth. And other future work includes finishing the database features. What we describe in the paper is that we've layered a database interface on top of a key value-based implementation. And as a result, the key value-based implementation is far more finished than the set of database features. So we're in the process of finishing up the database features. And in the future, we're probably going to have to improve the key value-based substrate to support richer query patterns that we'll see when we actually execute SQL queries. To conclude, making the clock uncertainty manifest in the API is incredibly powerful. To paraphrase Rumsfeld, a known unknown is much better than an unknown unknown. And we should be redefining our algorithms to make use of this known unknown. And I want to conclude with one final point. As systems have scaled, the tendency has been to go towards weaker semantics. And what this work shows is that, in fact, you can achieve stronger semantics at scale. Thank you very much.
All right, I see a lot of folks lining up, so let's do one question at a time, and then we can go back to the back of the queue.
Prince Mahajan, UT Austin. So when the true time assumption is violated, is it possible that the reads are not transactional for read-only transactions?
The reads would not necessarily be consistent across shards in the way that we described.
All right. Second question. All right.
Nicolas Schipper, Cornell University, and formerly at Google. I was wondering if you could comment on or compare external consistency with strict serializability.
I believe the two terms are equivalent.
Okay, thanks.
Jay Lorch, Microsoft Research. Excellent work. I just had one question. Why do you always assign a certain time to a transaction? Couldn't you benefit by sometimes saying this transaction happened sometime during this range by intersecting the beginning time and the ending time?
That comes down to our data representation. Remember, we store the data essentially indexed by the timestamp at which it was written. So that way, if you want to read the data at time 50, you look at time 50 and look back for the first piece of data that was written before 50. So if you had some slop in the interval, then you wouldn't know what data to actually read.
Thank you.
Masoud Moshe from USC. In slide 23, no, 23, do you know what happened in 10 a.m. April 13th?
Yes. So April 13th, 10 a.m., the reason we put this piece of data in is to show you the effect of increasing network latency on uncertainty. So what happened was 2 time masters in a data center were taken out of commission for repairs. And so the clients in that data center had to talk to remote time masters, and their uncertainty went up as a result.
Hi, Mark Chiarini, Harvard University. So is every epsilon only with reference to the local GPS readings or atomic clock readings? Or do you have some sense of a global reference epsilon?
Epsilon is computed, there's an instantaneous value of epsilon you get every time you evaluate the call to now. And epsilon is, in that sense, expressed as a value in, or an offset in global time.
So what if you've got worse regions with not as good GPS technology?
Right, so some data centers, because of the fact that their time masters are down, as shown here, might have greater values of epsilon when you ask for now, but the other data centers might have lower values of epsilon. And basically what happens is Spanner will slow down if you're running in the data center with higher uncertainty, and if you're in the data center with lower uncertainty, it'll run at full speed.
From aliyun.com. So I have one question. You mentioned that the chance of the clock go wrong is very slim, but what's the worst case scenario when it actually happens? So basically, even though it's a very low probability case, but if the damage is high, you still have to consider it.
Well, I think we need to consider, once you have a lot of machines, the CPU can go bad. So it's no longer the case that you can assume that your computer is actually a fully functional digital processor, right? So our argument is essentially, if you're willing to assume that the CPU is good, our clocks are just as good, if not better, right? Because you're basically assuming that your computer works. And when you have lots of machines, your computers won't work. But to answer the question more directly, this question was already asked. What happens is the timestamps are chosen in a way that don't guarantee external consistency.
Hi, Fitz Nolan, Yale University. I just wanted to make this concrete in my head. So you mentioned in one of your slides that I would take myself, or take somebody out of my friend list at time 6, and then I would be removed from their friend list at 8. So just in that interval, when I'm trying to make it so if I'm on like a web page and I, remove a person from my friend list, do I just wait then? Do I just see a blank screen? Does it look like network latency to me while they're making themselves consistent?
Sorry, I probably wasn't clear when I walked through this slide. So what is happening is that the two participants pick candidate values of S. And the coordinator picks 6, but it only actually computes the commit timestamp once it talks to all the participants. And then it chooses 8, and it commits at 8. They all commit at 8.
Okay, so then the user then just observes sort of nothing happens until 8. So there's a time there where nothing happens on the web page. Is that like a latency that the user experiences?
Well, it depends on the structure of your system. If you're constantly generating the web page at every clock tick, you'll see at clock tick 7, you'll see X is my friend and I'm X's friend. And at clock tick 8, then you'll see the behavior of the
right. So obviously it's negligible because it's so small, but if it were larger, you would just sort of see a hang or a...
I guess. I'm not quite clear on the UI model you're assuming.
Okay.